Okay. So, okay. So for some reason the recording didn't work properly. So uh, go. Let me just do a brief recap, and then I can continue. So initially, what I was talking about, I was talking about what is the equivalent spring constant when the springs are in series or in parallel. So here it is for when the springs are in series, we can find it in this manner. Suppose you have applied a force to it. There are two springs in series, and suppose the Ke is your equivalent spring constant. Okay, and you can calculate it very easily. Suppose this spring is moved by amount x, and this has moved by an amount y. So the force is equivalent force is minus K times x plus y. So now the same force is applied on spring 1 as well as in spring 2. So it will be equal to minus K1x equal to minus K2y. Now, now these three, they are equal. So suppose they are equal to C, some arbitrary constant, C, C not equal to 0, or you can say C is greater than 0. These are physical parameters. C is greater than 0. So now if you just do the simple calculation, you will find that 1 by Ke equal to 1 by K1 plus 1 by K2. Okay. And so suppose now if you have three springs, four springs, or n springs in series, you will simply find the equivalent spring constant using this formula. 1 by K equal to summation 1 by Ki. Now when the springs are in parallel, now similar displacement will be applied to all of the springs, and you just then need to just add those K1 plus K2 plus K3. Here Ke, if you have n springs in if you have total n springs in series, it will be Ke equal to summation I equal to 1 to n Ki. Okay. Now we are solving this problem. Okay. So this is the problem. Here you have mass m1 and here is mass m2. Now you have slightly displaced it. Not no there is no forcing no forces applied on the system. We will do the driving system later. So it is moved by an amount x1, x2 from its equilibrium position, and it is moved by an amount x1 from its equilibrium position. And this is the assumption that I am considering, that x2 is greater than x1. Now you are told to find the governing equation for this. So now for mass m2, this is m2. So this is the force is applied on this as you have moved by a small amount. So equivalent amount of force will be due to the Hooke's law, and it will be minus k2 into x2 minus x1. I have just written that m2 x2 double dot equal to minus k2 x2 minus x1. Similarly for m1, so in the last class that I have told that just opposite this sign, okay, because due to Newton's third law, okay. And for this, as these two are in parallel, so it will be k1 plus k1 minus 2k1 into x1. So these two are the governing equation. These two are the governing equation, and I have written it in the matrix form. Now you are told to find its it's the modal frequency. Okay, now we are doing that. Okay, so now substitute this. So it will be okay. So no. I have made another mistake. So sorry about that. So it will be divided by m2. This all will be divided by m1. It will be minus omega square. It will be minus omega square a1 a2 equal to minus 2k1 by m1. not x1, x2, it will be a1, a2. Now you take it to this side and calculate the derivative, calculate the determinant. Okay, so it will be omega square minus, zero. Suppose your omega square equal to alpha. So now this becomes in simple quadratic equation, and the expressions will be alpha square minus alpha times 2k1 by m1 plus k2 by m1 plus k2 by m2 plus 2k1 k2 by m1 m2 plus k2 square by m1 m2 minus k2 square by m1 m2 equal to 0. So these two will be cancelled. Okay. So now this will be, this imply alpha square minus alpha to k1 by m1 plus k2 by m1 k2 by m2 to k1 k2 by m1 m2 equal to 0. So alpha equal to minus b to k1 by m1 minus 8 k1 k2 m1 m2 divided by 2. Now if you do the calculation, the final, you will and then you will be able to find the solution. So I will just give you some outline of it. Okay, so now let us consider a case. So this is a complicated expression. So let us consider a case when k1 equal to k2 equal to k, m1 equal to m2 equal to m. Okay, so please check the calculation by yourself. There is a good chance that I am making some mistakes. Okay, so it will be 2k by m plus k by m plus k by m plus minus. So 2k by m plus k by m plus k by m. That means how much? That is 4k by m. 4k by m whole square minus 8k square by m square. 8k square by m square. Right? Divided by 2. So alpha equal to 4k by m plus minus of 8k square by m square divided by 2. 4k by m plus minus of 2 root 2 k by m divided by 2. So it will be 2 plus minus 2 k by m. So omega square equal to 2 plus minus square root 2 k by n. Okay. Now, if you fit this in this equation, assume that k1 equal to k2 equal to k and m1 equal to m2 equal to m, you will be able to determine the mode state. Okay. So yeah, so let's do that. So you need to feed those in this equation. So what is the final year matrix? So this is a determinant. So I need to just put, so in the matrix form I need to put this and calculate a1 a2. I need to find a1 and a2, right? So let's just do that. So case 1 is omega square equal to 2 plus square root 2 k by m. So your equation will be this. So what is your equation? Omega square minus 3k by m and k by m, k by m, a1, a2, 0, 0. So you will put this here. So it will be square root 2 minus 1 k by m, k by m, k by m, 1 plus. Okay, so what is your 0? So you can take a1 equal to 1 and a2 equal to 2 minus 1. Okay, so this is a complicated this is a complicated modal shape that you can easily see. Now if you substitute this in equation, it will be 1. Okay, so yeah, so you can see that there is probably I have made a mistake somewhere. Okay, so what you do that this so the governing, I have made a mistake here because when I am getting this expression, then it should obviously satisfy the second expression. Okay, and it will be only satisfied. Just a second. So how can I write this? It will be so equal to 1 by 1 minus square root 2 equal to minus of 1 plus square root of 2. So, yeah. So you can see that from this expression that I am getting, one is a1 equal to 1 and this is minus of 1 plus square root 2, and obviously if you substitute it, it will not give you 0. So there is the error of plus minus error. So find, so just try it at home and you will be able to figure that out. But the main thing is the governing equation and this this matrix equation. Okay, when you set the governing equation, then other things are just following the procedure. Okay, just try that, or I will do it in the I will do it to give you the correct solution in the next class. Okay. Okay, so let's move to the second question. That's the thing. Right. So suppose you are pulling a spring like this. Here it is a mass. So wrist length of the spring is L naught, and also here is L naught. Okay, and after stretching, its length become L. Now this is provided thus this angle, it makes it angle theta with the horizontal axis. This displacement, this is z of t. Now you need to find what is the governing equation for this question for this system. So yeah, and its mass is m and spring constant for both of these is k. So you can very easily see that this is a very easy system. Okay, so you so when you so this so it indicates that these two springs are somewhat in parallel. Okay, so if you just pull it, both of the spring will be stretched by the same amount. Okay, because you are uh, doing according to this z equal to, suppose if this is z equal to 0, if we're doing from this height. Okay, and another is this is 2a, and this is just the midpoint. Okay, this is minus a, this is a, x equal to 0. Okay, so this is just at a midpoint. Okay, so both of the springs are stretched by the equal by an equal amount. So what will be the governing equation? This is very simple. So you just need to do mass balance, sorry, force balance on the spring. That so what will be the amount that is getting stretched? That is, it is mz double dot. That is the acceleration in the z direction. And due to the Hooke's law, what will be the force acting downward? What will be the force? It will be simply minus 2k. 2k because there are two springs. Okay, that's why it is 2k. Then change in length of the spring, change in length of the spring, L minus L naught into sine of theta. Okay, why? Because I am moving in the vertical direction, so I need to take so here suppose you have a spring, so here the change increase in length is minus L in minus L naught, and for the Hooke's law, F equal to minus k into x. Here x is your change from the equilibrium position. Okay. Now it is changed along this direction. Okay. This is not the vertical direction, so you need to project it to the vertical direction. That's why the sine theta. So it will be the coordinate equation will be mz double dot equal to minus 2k L minus L naught into sine of theta. Okay. I hope this is a very simple calculation. Okay. Just do the free body diagram and this will be clear to you. Now let us solve some other problem. Okay, suppose you have this kind of a combination. So this is a string and its string tension in the string is 2k L. Its length is L. Alright. Now it has spring constant K and this object has a mass of M. Similarly, this has also spring constant K. Sorry, spring constant 2k and mass equal to 2m. Now you need to find the eigenvalues. Sorry, you need to find the governing equations, the eigenfrequencies, and the modal shape for this system. Okay, so let's do it. So how to analyze this problem? Okay, one thing that you can do by from symmetry, you can say something that if you push it by the same amount, you can get one frequency. That will obviously be one mode. Okay, that both are getting pushed if it is increased by some amount, and so as a result it will be decreased by the same amount. This can be one mode, but there are two masses. So there are um, uh, two modes, two possible modes that can be present. What can be another mode? Another mode can be if you push it by some amount. It also here if you give it a similar amount. Okay, that can possibly be another mode, but we have to find out. So let's do it completely general. So let's move it by an amount, say x1, and this by amount x2. Okay, and just a moment. And we can assume that x2 is greater than x1. Or do it opposite. x1 is greater than x2. So what will be the shape? The shape will be something like this. It is stressed. No, I will prefer this. I will tell you why. This. So now the shape will look something like this. Okay. So I need it because I want. So obviously this tension, this string, it will be not a vertical. There will be some vertical. We need to calculate some vertical component. So there will obviously be a theta. So my I want my this is the so if this is the triangle and this is an angle theta. So I want my base to be at the top. So that's why I take that x2 is greater than x1. Mm, sorry. So that's why x1 will be greater than x2. Okay, so this is the assumption. Okay, so now for this for mass 2m. Okay, here it is pushed. We are pushing it by amount x1. So obviously, if opposite force will be acting on this, so m x1 double dot equal to minus 2k x1, and there will be some component coming from the string. So this tension is acting along this direction t. So if I define it as theta, so there will be t cos theta force acting on the horizontal axis plus 2k L cosine of theta. And now what is cosine of theta? If I do this what is this amount? This amount is x1 minus x2, right? So it will be x1 minus x2. Just a second. Yeah. Let's yeah. Let's do the assumption. Let's do the approximation like this. Your x2 is greater than suppose x1. Okay. So this is a straight string. It is stretched by an amount x1, and it is because initially they are at the same horizontal position, and it is moved by amount x2. So this is your x2. Okay, so this bay height, this distance is obviously x2 minus x1, and that is my theta. Okay, yeah. So now it will be minus 2k times x1 plus 2k L into x2 minus x1 divided by L. If we just cancel it out, so your equation will be, so it will be 2m x1 because the mass is 2m. So minus 2. So if you just do the calculation, you will find it will be minus 4k of x1 plus 2k x2. Now you divide it by 2m. So x1 double dot will be equal to minus 2k by m x1 plus of k by m x2. This is your equation 1. Okay. Now, so previous, okay, so I will tell it later. Now, directly from intuition, you cannot say what kind of movement that what will be the possible modal shape. Okay, because here the spring, this system is not symmetric. The system is not symmetric in the sense that if it is k and it is m, and it is also k and it is m, then we can say the system is symmetric. Then our intuition, then our intuition will be easier. But here the system is not symmetric, so your intuition always might not work, as you will see you will see here. So after that, I will solve the exactly same problem by, but then I will consider a symmetric system. Okay, that I will take a k, and in here the spring constant k and the mass m, and you can see the difference there. Okay, so now let's proceed with this. So now for this mass, for this mass m, so what will be the force? So now obviously, so it is pushed in this direction, so the opposite amount of force will be acting in the here in direction, and for this, the tension will act in this direction, and this was theta previously, so we know that this will also be theta. So the horizon, so from the tension of the string, the force will act on the negative x direction. Okay, so the movement, so its governing equation will be m x2 double dot equal to, so I can directly write minus 2k L cos theta. This is just coming from this. This is just, I am just using the Newton's third law of motion, and minus k x1. Okay. Uh, just a moment. Huh? Hello. 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 Yeah. नहीं wrong number. So if you calculate this, you will find that the governing equation will be x1 mm, it will be minus kx2, and this will be the governing equation. Okay, so now you have two equations. One is x1 double dot equal to minus 2k by m x1 plus k by m x2, and x2 double dot equal to 2k by m x1 minus 3k by m x2. So now you need to find the modal frequencies for this system. Okay, so x1, x2, will be driven I omega t. Okay, so now if you just substitute it, so I am directly writing down the matrix. Okay, it will be omega square minus 2k by m, k by m, 2k by m, and omega square minus 3k by m, e1, e2. Okay. So, this will be your matrix equation. Okay. Now, for the non-trivial solution, the determinant needs to be 0 here. So if you calculate the determinant, you will find omega square minus 2k by m, omega square minus 3k by m, minus 2k square by m square. So you just solve it, you will find that omega square equal to 4k by m. This is a very simple quadratic equation, and k by m. Okay. So omega equal to 2 square root of k by m and square root of k by m. So these two are your modal frequency. Alright. Now you need to calculate. Moment. Just a moment. Huh? Yeah, sorry for the interruption. Alright. So now you need to calculate the modal shape. Okay, so you just need to this formula, put it here. So now let's study case by case. So there are two cases. So case one, that is omega square equal to 4k by m. So one intuition was if you move it by, so this is your string. Okay, one spring is attached here and another spring is attached from here. Suppose if you move it by an equal both the spring in the same direction, so there can be that is one possible mode. And if you move it by the opposite direction, that means just like this. Okay, so that can be another possible mode. Now let's verify that. So when omega square equal to 4k by m, so it will be 2k by m, k by m, 2k by m, k by m, a1, a2 equal to 0. So what can be one possible solution? that a1 equal to 1, a2 equal to minus 2. Now let me draw the spring again. Sorry, the entire system again. So understanding this is very important. So to get the insight clear about this subject, you will find, so you will see that these two are the eigenvectors. Okay, so we are using the concept of linear algebra in solving the mechanical problem. Okay, so and these eigenvectors are giving you the shape, so how you should part up the system. So this is a1 is related to this. It has a mass 2m and spring constant 2k. It has a mass m and spring constant k. So it says that if you move it here in this direction by an amount x, and you move it by an amount 2x, okay, in the opposite direction, then you will get this frequency. So our intuition is correct. So that means what will be the shape of the spring? Initially it is like this. Now it will be something here. It will be one spring, and here there will be another spring. Okay, so obviously if you stretch it in the opposite direction, obviously the frequency will be higher. Okay, as a result you get this frequency. So one intuition is correct, but what is incorrect, that we have assumed that it should be equal frequency, but it can't be equal frequency, right? Because it has a different spring constant. So it is and also a different mass. So it is affecting the system. But the direction was correct. So one would be in the positive direction and another would be in the negative direction, the perturbation for for this larger frequency. So now for the smaller frequency, okay, that is case 2. So it is omega square equal to k by m. So if you put the values, so it will be minus k by m. I'm just putting k by m here in this equation. Okay, k by m, 2k by m, and minus 2k by m, a1 a2 0. So here obviously a1 equal to a2 equal to 1. That means you are again draw. Let me draw this. No. So that means you are pushing by the same amount. You are pushing it by the same amount. If you just do this, then your average, then your modal frequency of the system will be k by k. Okay, so this is, so although it has a spring constant 2k and mass 2m, and it has k and m, okay, finally they will oscillate with a frequency of k by m. All right. Now let's solve exactly the same problem, but here, but now consider a symmetric problem. Okay, symmetric problem means now instead of 2k and 2m, I will consider both of the spring has same spring constant k, and both of the masses have same mass m. Okay, so then let's redo the problem. All right, so give perturbation x1, give perturbation x2. So what was my previous assumption, that x2 is greater than x1, that x2 is greater than x1. So shape of just like the same problem. So last time I got confused about this x2 or x1, which will be greater and what should be the shape. Not now. If x2 is greater than x1, so it will be moved further. compared to x1. So as a result, this is x2 minus x1, this length. So for this, this is suppose mass 1, mass 2. For mass 1, the governing equation is mx1 double dot equal to minus of k x1. This is the spring constant 2k L. Sorry, this is the tension that is in the spring plus 2k L times cos theta. This is theta. It will be x2 minus x1 by L. Cancel it out. It will be minus 3k x1 plus 2k x2. Yeah, this is correct. Now let's do it for the second mass. So obviously one will be minus k x2, and as it is positive here, so obviously for this spring it will be, for the second mass it will be negative. So it will be minus 2k x2 minus x1 equal to 2k x1 minus 3k x2. So I will, so there is, so can you see a pattern is forming here? So previously the system is not symmetric. The system was not symmetric. As a result, you can see that your matrix, the governing matrix, that is not symmetric as well. So here it is minus 2k by n, k by, here it, you can see that aij is not equal to aji. So a12 not equal to a21, because the system itself is not symmetric. How can you expect an symmetric matrix that is defined governing your system, right? So now the system has become symmetric. As a result, you can see that the governing equation x1 double dot equal to minus 3k by m x1 plus 2k by m x2, okay, and x2 double dot equal to 2k by m x1 by x2, right? So you can see that here this term, they are equal. So if you further, so you define a matrix, so it is a symmetric matrix. So let me write this. Because your system itself is a symmetric, is a symmetric system, right? So now what is left? You need to find its modal frequency, and after that you need to find its modal shape, right? So let me do that. So first let me write the matrix. Here A1, A2 are the eigenvectors. Okay. Now you will substitute it in this equation and take it to the right hand side, and finally you will get this expression omega square minus 3k by n 2k by n 2k by n and omega a1 a2 0. Now to get a trivial solution, you need determinant of this matrix has to be 0. So you will get omega square minus 3k by m whole square minus 2k by m whole square equal to 0. So one solution will be omega square minus 5k by m. So omega minus 5k by m, omega square minus k by m. So one possible solution is omega square equal to 5k by m k by m, right? Now, if, so now case one. Just a second. Just a moment. Okay. Now, the case one is omega square equal to 5k by m. Okay. Now you substitute this in equation. What will happen? You will get a equation of the form 2k by m, 2k by m. So a1 equal to 1, a2 equal to -1. That means you need to move those masses in the opposite direction by the same amount. Okay, then you will get this larger frequency. This is expected. Now for case 2, that is omega square equal to k by m. That is, it will be minus 2k by m, k by m, minus 2k by m, 2k by m, 2k by m, and minus 2k by m. A1, A2. So here the solution will be A1 equal to 1, A2 equal to 1. So you can see that when sorry, so you can see that when your system is symmetric, just by intuition you can say that how your what will be your modal frequency, what will be your modal shape, and from the from that intuition you can very easily calculate your modal frequencies. Okay, but when the system is not symmetric, like in the last class, so you can predict you can predict your modal shape, you can predict your mode shapes, but it may not be accurate. So last time we have also guessed that it will be either on the both on the same direction in the opposite direction, but we couldn't measure the value. It was for the same direction, both will be moved by a same amount, but the opposite direction, one will be 1 and another will be -2. This prediction cannot come from the intuition. You need to solve the entire problem. Okay, for that. But when your system is symmetric, when you can very easily take this guess and do the rest of the calculation. Okay, all right. Now I will give you another problem. Suppose, so I think this is an old assignment. Just 1 second. Okay. So suppose you have an equation like this, that del square u del t square equal to some vp square del square u del extra square. Okay. Now we know that if any solution of this kind, x minus vpt will be solution of this. Okay. But suppose suppose you are given with some option. Okay. Then what is the most general solution of an equation of this kind? This is the wave equation. Now I'll give you four options. You need to find what is the most general solution. Okay. So now, so suppose you are provided with three options. Okay. And you are told, so what is the correct solution? Okay. Now, so how to proceed? So now, first of all, just a second. I just need some water. So At first, you should inquire that what is the meaning of this summation? Summation m equal to 1 to infinity. Okay, because if I don't put as infinity, if I don't put a summation sign, then would it not, then will it agree this solution or not? Will it agree this equation or not? Okay. The now if I don't put any summation sign, then one or two if any of the solutions are correct, they will definitely agree this equation. But that is not the most general solution. You are required to find the most general solution. Okay. Now the summation means that all of them individually can satisfy can satisfy this equation. Also their summation, okay, because this is a linear equation, and their summation, and this is a property of linear equation, that this is suppose L is your linear operator, and u1 and u2 are some solution of it, then you can write it as L of u1 plus L of u2. Just think about in this way. Suppose mm, d square dx square e to the power 2x, or just d dx, plus e to the power of 3x. Okay, so what will be the result? Equal to 2 into e to the power 2x plus 3 into e to the power 3x. Very simple. So we can write it as d dx of e to the power 2x plus d dx of e to the power 3x. So here ddx is like L. This is a derivative is a linear operator. So ddx is a linear operator. It is u1 and it is u2. So it is working on u1 plus u2, and it is giving you result L u1 plus L u2. Similarly, if you have a solution linear operator L and u is any function, if you multiply with some scalar, here c is belongs to r is the real number, then it is c of lu. Okay, that means ddx of 2 into e to the power 2x equal to 2 into the power x equal to 2 multiplied by ddx of e to the power x. Okay, here we are exactly doing the same thing. Sine omega mt plus sine omega 1t plus sine omega 2t plus sine omega 3t, just like u1 u2 u3 etc. And here am, that means a1 a2 a3 are the like c, that are the scalar multiplier. Now if you combine this rule, suppose this is rule 1, or suppose this is your r1 and this is your r2, this is the addition rule and this is the scalar multiplication rule. Now if you combine this r1 and r2, so what will be the case result? L of c1 u1 plus c2 u2 is equal to c1 lu1 plus c2 lu2. So it is called the linear combination. So individually u1 u2 are solution. Okay, individually u1 and u2 are solution. But here we are taking the most general solution. That's why we are taking the linear combination. If u1, u2 satisfy some equation, then its linear combination, if the operator is linear, will definitely satisfy the equation. Okay, so that is the idea. That's why we are taking m equal to 1 to infinity. So now how to solve this? So the first hurdle is understanding this, the most general solution, and why. Then what is the issue with this summation sign? The next step will be how to solve this. Okay, so it is discussed in class that you can solve it by considering uxt equal to some f of x into some t of t. I will not solve that thing. You just check the lecture and you will find it and practice it. Now So what can be the, so we know that in the last lecture we have discussed that if this is a wave equation, and any equation of this kind will have solution u of x minus vpt, right? And here we have defined as omega m equal to vp km. Then we have defined it some parameter. Now, so we can see that if this equation has a form like this. Okay, this equation has a form like this. Hmm? So now, if you take km as constant, okay, and if you divide it by omega km, so it will be, you can modify it to some x minus vpt. You can you can, so, and also x plus vpt. Similarly, cosine, similar, the same thing will happen for the cosine. So this is obviously a solution for this. Okay. Now here you have some combination of sine omega. So let us discuss this. Okay. Suppose here you have a combination like sine omega mt and multiplied with sine kmx and kmx, cosine of kmx. Let's, for a moment, just forget about this and let's concentrate on this sine omega mt multiplied with sine kmx plus dm cos kmx. Okay, so the combinations will look something like this, as sine omega mt into sine km. Now, if you use the trigonometric formula sine A sine B equal to half of cosine A minus B A plus B, right? Similarly, sine omega mt, so it will be half of cos. If we can write it as x minus vpt minus cos of x plus vpt, right? We can project it in this way, and sine omega t and cos kma, it is half of sine. It is just like sine A cosine B. So it will be just half of sine A plus B plus sine A minus B. So if you just substitute it with omega n and km and rearrange it, it will get an equation like this. So this is also a solution. So without solving it, just by looking at the solution and just from intuition, you can find this result. Now for this, okay, it will be some one, there will be some constant term one, okay, and say one omega squared t is one minus half of one minus cos 2 omega t, right, divided by 2. Similarly it will happen for this. Now it will be multiplied with sine kmx and cos kmx, so there will be term like sine kmx and cos kmx, right? So that is not a solution for this. Also, there will be some combination of sine kx into cos 2 omega t. It will give you some result, but that will be not a solution for this kind of equation. Okay, so only option A and option C are the correct choice for this equation. So just from the your basic knowledge of a wave equation, and just by looking at the solution and your basic knowledge of trigonometry, you can very easily solve this problem without we you can very easily answer the question without even solving it. Okay. Okay. Right. So in the next class we will discuss about the Jacobi elective function. Okay, But today we today I will not start it. In the next class, we will discuss about the Jacobi electric function, and then we will solve many questions regarding that. But today, let's start with the nonlinear oscillator. Okay. So what is a nonlinear oscillator? The basic example of your nonlinear oscillator is your just simple pendulum. What is the equation for it? Equation for it is m x double dot plus, I think it has equation like x double dot plus omega square sine x, right? Here omega square is g by l, something like that. Okay, you can find it. But this is the basic structure of your pendulum equation. That if your displacement is x, the equation is x double dot plus omega square multiplied by sine x. Now this is a nonlinear equation. So in the first lecture we have talked about it, that here this is sine x. So in our class 2 course, we always assume that if your displacement is small, we assume sine x as x. Why? Because sine x we can write as approximately x minus x cubed by factorial 3 plus x to the power 5 by factorial 5 plus dot dot. Okay, this is the series expansion for sine. Now when x is very small, we can approximate with it with x. Okay, so when x square plus omega square x equal to 0, then we can very easily solve this equation. But but the solution is not very easy for this kind of case. That's why we need to use the Jacobi elliptic function in order to solve it. That we will do in the next class. But now, what can we analyze from this? Okay, suppose you have an equation like this. Mm, So, by some any reason, can we estimate some of the feature of it? Some anything? Mm, I mean, it is not integrable with time with respect to because we have equation d2x dt square plus omega square sine x equal to 0. It is integrable but you have to use some special kind of thing. But in from our general mathematics knowledge, we cannot do anything with it. We know how to solve d2x dt square plus some function into x equal to 0 when this is linear, right? But this is a non-linear equation. So let us do one simple thing, that multiply it with dx dt, x dot. Okay. So if you multiply it with x dot, what will happen? So x dot x double dot plus omega square sine x into x dot equal to 0. Now, can I write it in this way? Just check this term, x dot x double dot. Can I write it in this way? So let's verify. So d dt of half x dot square. X dot is itself dx dt. Okay. So it will be 2x dot multiplied by d x double dot divided by 2. So it will be x dot x double dot. So this is correct. Now plus omega square into sine x into x dot. Can we write it in this way? d dt of minus of cos x. So what is d dt of minus of cos x? So what is ddx of cos x? It's minus sine x. And I am doing d dt. So that means d dx of simple chain rule into dx dt. So equal to sine x multiplied x dot. So it will be 0. Okay. So you have got an expression d dt of x dot square minus omega square cosine of x equal to 0. Does this, so is this term familiar to you? Do you, so what I can do, let if I define x dot equal to v, obviously if x is position, the x dx dt x dot is the velocity, so it is half v square minus something. So can I write this is the kinetic energy and this is the potential energy, and so this summation is the total energy. So d dt, and we know that from the conservation of energy, if there is no viscosity in the system, okay, the total energy is 0. So we can define it a total energy for this system. For our pendulum, we can define a total energy like this, and we can draw. So we can define our total energy as half of x dot square minus omega square cos x. This is equal to constant, as we do not have any viscosity in our system, right? So although we cannot solve this equation from our basic mathematics knowledge, but still we can extract some information from it. We can extract the total energy, and from the total energy we can calculate the evolution of our pendulum, okay, of our nonlinear pendulum, okay. So yeah, so this is the idea. Now suppose you have an equation like this. Mm, so this is the last problem that I am going to solve today. Now if you have some viscosity in your system, some damping, so there will be a term like b dx dt plus. Okay, then this calculation will not be that easy. Okay, you can try that. Then if you find some, if you have viscosity in your system, then it will be difficult to calculate energy like this. Okay, now take us another example. It will be difficult when viscosity is present, because uh, we are multiplying it with x dot, and it is already bx dot. Okay, so it will be bx dot square. So ddt of what will give us bx dot square? X dot. So that is the difficulty. Okay, so when the system is inviscid, then we can very easily find its total energy and do some analysis on that. Okay, even though you cannot solve it completely. Now let us consider another system. So this is the last example that I am giving you today. That is theta double dot t plus omega square theta t plus alpha theta q equal to 0. So this is called a nonlinear oscillator. This is a nonlinear oscillator problem. Okay, and you need to find its total energy. What is the expression of its total energy? The idea is exactly the same. Okay, you multiply it with theta dot and do the rest. So if you restrict it up to this, then you will get simple linear oscillator equation. But now you have incorporated this term. Okay, so the feature will be different. And from our basic school level mathematics knowledge, we cannot solve this. Okay, so now let's calculate its energy. So multiply with theta double dot plus omega square theta dot into theta plus alpha theta dot theta cube equal to 0. So this implies d dt. Writing it. So I am writing it inside d dt. I'm writing the total expression. So it is just like the last example. Half theta dot square plus half omega square theta square plus alpha by 4 theta to the power 4 equal to 0. Just verify it. You will see that this is the correct answer. So here this is the kinetic energy because it has half v square. This is the potential energy, and ddt of and ke plus p is your total energy t, and ddt of your total energy is 0 because there is no viscosity in your system or there is no damping in your system. So it is just showing that energy is conserved. Okay, so what will be the expression of your total energy? Half of theta dot square plus half omega square theta square plus alpha by 4 theta to the power 4 equal to constant. Okay, so this is your total energy. So, and we can extract information of the system using this energy equation. Obviously, we can plot it and play with it and get the information about system. But in the next class, uh, we will solve this kind of equation, and we will know what is Jacobi elective function, and we will solve the problem of this nonlinear pendulum tracking oscillators. If you solve this equation, the nonlinear pendulum, then you can solve the Duffing oscillator equation. Why? Because if you expand this term sine x, it is x minus x cubed by factorial 3. And here you can see that similar kind of terms are present. This is this. Theta is present and theta cube is present. Okay, so if you solve this equation, then you can solve this equation, that nonlinear oscillator equation as well. Okay, so in the next class we will solve this from the so in the last class and today also we have mostly solved the linear oscillation problem, and from the next class onward we will go to the nonlinear oscillator equation. Okay, and I will share my recorded video and this notes with you. So good night.